All right, welcome. So today we're going to be talking about atomic equations, and I'm going to work out a few examples for you so you can see how to use the equations to find energy, wavelength, and frequency of light. So for the first question, it asks, what is the wavelength in nanometers of light with a frequency of 3.75 times 10 to the 14th seconds to the power of -1? First off, don't worry about the unit that's attached to the frequency. That seconds to the power of -1 is not an exponent or anything, it is simply a unit. All that means is that our frequency is 3.75 times 10 to the 14th power waves passing by per second. That is a given frequency, so we are starting off with a known value for f, for frequency. The question asks, what is the wavelength? We have to find lambda. So lambda is the Greek letter that represents wavelength, and that's what we need to find. In our notes today, we went over several different equations that we can use to calculate energy, wavelength, and frequency. Once we've identified the known and the wanted variables, we need to choose the appropriate equation that has both of those variables in it. So if I look at the equations from class today, we have three possible equations that we can use. We have the speed of light equation, which tells us that the speed of light is the product of frequency and wavelength. We have an energy equation that tells us that energy can be calculated by the product of Planck's constant and frequency. We have another energy calculation that allows us to calculate energy by taking the product of Planck's constant and the speed of light and dividing it by wavelength. Each of these equations has different variables in it, and we need to choose the equation that's appropriate for our problem. Since we were given frequency and wavelength, we have to choose the equation that has both of those variables in it. And the only equation that has both of those variables is the speed of light equation. So that's going to be the equation that we use to try to solve this problem. Once we've chosen the appropriate equation, we need to go ahead and put the known information in and substitute numbers for some of the variables. For C, we always have that value. The speed of light is a constant value, and it's always 3.00 times 10 to the power of 8 meters per second. We don't have to put the unit in algebraic equations, but we are going to put parentheses around that scientific number. Any number that's written in scientific notation needs to go within its own set of parentheses in your calculator. Then we have the equal sign, and on the other side of the equation we have frequency, which we were given a value for. It's 3.75 times 10 to the power of 14. And again, the unit was seconds to the power of -1, but since this is an algebraic equation, we're not going to put the unit in. Then we have to multiply that by lambda, which is wavelength, which is our unknown. So since I don't have a number value to plug in there, I'm just going to put lambda. To solve for lambda, again, we have to use some basic algebra. And if I want to solve for lambda, I have to get it by itself on that side of the equation, which means that I need to divide both sides of the equation by 3.75 times 10 to the power of 14. That's going to isolate lambda on this side of the equation, and by doing that on the other side of the equation, by taking the speed of light and dividing it by that value, we'll calculate lambda. The issue is not within the problem itself. The issue is in the question. It asked us to give an answer in units of nanometers. In these equations, the wavelength is always going to be in meters. You always have to plug in a value in meters for wavelength, and when you do the calculation, you will always get a value in meters as your answer for wavelength. So when I take 3.00 times 10 to the power of 8, and I divide that by 3.75 times 10 to the power of 14, the answer that I get in my calculator is in units of meters. And so my wavelength is 8 times 10 to the power of -7 meters. However, we needed that in nanometers. So when we need to convert from one unit to the next, it's time to use dimensional analysis. The conversion factor I gave you in the notes is that 1 meter is equal to 1 times 10 to the power of 9 nanometers. So I'm going to use that conversion factor. 1 meter is equal to 1 times 10 to the power of 9 nanometers. Again, my units cancel out from top to bottom, and now my answer is going to be converted to units of nanometers. So I'm going to take my answer and I'm going to multiply it by 1 times 10 to the power of 9. And I end up with a value of 800. Since my given value had 3 significant figures, I'm allowed to keep 3 significant figures. So I'm actually going to put a decimal on this value to make both of the zeros at the end of this value significant. And that's going to be the answer to number 1. For the second problem, it asks again for a wavelength in nanometers of light with an energy of 2.25 times 10 to the negative 18th joules. So again, I need to find wavelength, but this time I'm given a different variable as my information. My known value is 2.25 times 10 to the negative 18th joules, and joules are the unit for energy. So I have to choose the appropriate equation. I'm given energy, and I'm being asked to find wavelength. So I'm given energy, and I'm being asked to find wavelength. The only equation that has both of those variables is this last one. So this is going to be the equation that I use to solve this problem. So E equals hc over lambda. I then need to start substituting values in this equation where they belong. Energy was given to us. It's 2.25 times 10 to the negative 18th power. And again, I'm not using units because this is an algebraic equation. When we do dimensional analysis, units are necessary in our calculations. For H is the symbol for Planck's constant, which is 6.63 times 10 to the power of negative 34. I need to multiply that by the speed of light, which is 3 times 10 to the power of 8. And then that's going to be put over lambda, which is my unknown. So now we need to think about how we're going to algebraically solve this problem. First off, I see some multiplication. So I'm going to go ahead and multiply those two values. And again, I put them within their own set of parentheses. 6.63 times 10 to the power of negative 34 multiplied by 3.00 times 10 to the power of 8. Gives me a value of 1.989 times 10 to the power of negative 25. I'm going to keep all of the digits in that value because we're not at the end of the problem yet, so it's not appropriate to round yet. Once I've gone ahead and done the multiplication, I need to start the process of solving for lambda. And the way that this problem is set up, I see that I have a proportion here. And the easiest way to do things when you have a proportion is to make sure that you have proportions on both sides. So what I do is I take my energy value and I put it over the number 1. Mathematically, that doesn't do anything at all, but it does allow me to see proportions on both sides of the equation. And once I see that I have proportions on both sides of the equation, I can use the butterfly method to solve for the unknown. So what I'm going to do using the butterfly method or cross multiplication method is I'm going to multiply the two numbers that are diagonal from each other in the proportion. So 1 times 1.989 times 10 to the negative 25th. That's going to go ahead and keep that value the same. After that, what I do is I divide by the number that was left out of that multiplication. So the third value is what I'm going to use to divide. So I'm going to take that product, my cross multiplication product, and I'm going to divide it by 2.25, and again, it needs to be within its own set of parentheses. 2.25 times 10 to the power of negative 18. And when I do that, I've gotten an answer for wavelength. So my wavelength is equal to 8.84 times 10 to the power of negative 8 meters. Again, anytime I get an answer out of an equation for wavelength, it's going to be in units of meters. Anytime I put a value for wavelength into an equation, it needs to be in units of meters. Unfortunately, the question asked for nanometers again. And so what I need to do is dimensional analysis again to convert this to nanometers. So 1 meter is equal to 1 times 10 to the 9th nanometers. Again, my units cancel out, and after I multiply my wavelength in meters, so 8.84 times 10 to the power of negative 8, I'm just going to leave that as my answer for my previous calculation. I need to multiply that by 1 times 10 to the power of 9. And that's going to convert my answer to units of nanometers. So I end up with 88.4 nanometers as my answer. That has 3 significant figures, which is the same number of significant figures that we started with in the problem, so there's no need to round. This is how you solve problems using those atomic equations. You're using a system of algebraic equations where you simply either multiply or divide. And you also at times may need to use dimensional analysis to convert from meters to nanometers or vice versa. But using these skills, you guys should be able to answer all of these questions.